So I'm going to talk about some results of pebbling and algebraic systems and systems. First, talk about pebbles, pebble games. Yes. So the normal pebble game is one player game played directed graphs, and we will have a unique sync, and typically this player has a set of pebbles. They can be white or black, and the idea is follow some rules that pebbles configuration so that starting from the empty configuration, you reach some other configuration. And there's several versions of the game. So the most general one, the one thing I'm going to talk about, is this so-called black-white pebble game. Here, the player has black pebbles and white pebbles. And there's some rules for placing them. Black pebble can always be placed on a source node or a node whose all predecessors have pebbles on them. A white pebble who simulates non-determinism can be placed on any vertex, but can only be removed if all the predecessors have pebbles on them, either white or black-white pebbling of a graph G. So will be starting from the empty configuration, reaching the empty configuration at some point, putting a pebble in the sink. In the black pebble game is a restriction of the other game, in which only black pebbles are. But only, and there's another version of the game I want to talk about, the reversible pebble game. Is a restriction of the black, so it's a game, which in order to remove a pebble, the black pebble, also the predecessors of that pebble, of that vertex, need to have a pebble. So, and there's, this pebbling is having very useful in complexity in all fields, because somehow the pebble properties of the graph translate, or the pebble measures, to other complexity measures. So we consider basically two measures here, time and space. Time is how many steps you need in order to reach your goal, and space, what is the maximum number of pebbles that you need at some point. So use simple example. Something I forgot to mention that's important. I think that a black pebbling is only allow black pebbles, and but this you can use the dual system of a white pebble, in which we only allow white pebbles, and you can see that white pebbling only is exactly the same as the black pebble, but looks the other way around. So whenever you change the order of the configuration, so if you have this black pebbling, if and only if changing the order of the configuration, you get a white pebbling of G. We'll see that in a minute with this example. So here, see first a black pebbling of the pyramid. These are the sources we're pointing up. So the pebble here is the source, not the source. Now both descendants of this have the predecessors have a pebble, so we can put a pebble here. At this point, we have three pebbles. Take this way. The black pebble can take it away. Put it here. Another pebble here. Here we need 4. Then we can take this way, and then we can put a pebble here. and if we want to empty it. So this was some number of steps, and at most 4 pebbles. And we can see that also in the same way, going backwards, if we start by putting a white pebble in the sink. This is a white pebble can always be away, and now we have to empty this graph. So for this, we can put the pebble here, the pebble here, and this is exactly, probably you don't remember, but this is exactly the same slides that I took, but changing the order and putting white pebble instead of. So all the parameters between black and black are exactly this. Here, then we can remove that. Okay, so what is the relation with between pebbles and proof complexity? It goes to this so-called pebbling formulas introduced by Susanna F. So for any direct acyclic graph G with a unique sink C, we make a variable xb for every vertex and use the following clauses to encode an unsatisfiable form. For every vertex, if all the predecessors of the vertex, I mean, this variable is 1, it's a pebble on vertex B. Then that means. So if all the predecessors have a pebble on them, then we can put a pebble. And we also say that this sink axiom will include the sink axiom, saying that they cannot be a pebble C, and you can see that these two things are incompatible. So if you, in particular, the first axiom for the sink, there's no predecessor, and for the sources, there's no predecessor, and then we have sources are true. If variable is, if all the predecessors of a vertex are true, the vertex is true, and the things is true. This is a contribution. And polynomials, we introduced that. We translate in this, the standard way, and it's interesting that all these axioms have at most 2 monomials. So I'm gonna have some connections between these games and the algebraic systems, which have been here mentioned several times. I'll go for them. Nullstellensatz, refutation, it's just a set of polynomials that add up to 1. And this is usually considered as a static system, so one-shot system. You have the polynomials P1, Pm, and you give this other polynomials P1, plus. More general and more dynamic is the Polynomial Calculus that you apply, and with these two. And this refutation is just a sequence of polynomials that can be derived in a standard way, like a standard proof system. Less known is something between. It's called the Monomial Calculus. This calculus was, or this proof system was introduced by Christopher and Martin, and identifies exactly the complexity of graph isomorphism formats. Meaning by that they prove that the degree of certain refutations exactly characterizes something called the Weismann-Lehmann dimension of the graphs. So by showing that it's a natural system. So it's like saying you have a complete problem for a complexity class, then is the natural complexity class, or a natural problem in the class. And the only difference with polynomial calculus is that the multiplication rule is only allowed to be applied P when P is a monomial or the product of a monomial and an axiom. So in general, polynomial calculus, P can be any polynomial. And as they also notice in the paper, Nullstellensatz can be considered in this sense, in this unifying way, as a system like this, by restricting even more the multiplication. So all these three systems have linear combination rule, and multiplication, that is for Nullstellensatz, can only be applied when P is an axiom, or say you multiply an axiom times a variable and then another variable. So it can be also a monomial times an axiom. Monomial calculus can the same thing, an axiom, or if you have derived a monomial, you can multiply this monomial also times. And polynomial calculus, unrestricted. So this makes a little hierarchy of proof systems in the same way as we had a little hierarchy of pebbling games. So there are some, okay, the complexity measures that we use, degree, the size have been already defined. Actually, for size is usually for Nullstellensatz is defined in a little different way. Doesn't really matter. But the point is that since now all these three systems can be seen as dynamic systems, like you're making deriving monomials or polynomials and so on and multiplying or doing linear combination. One can consider also space measures. So you can consider a configurational proof in that you have a configuration is just a set of polynomials, and in each step you can either add a monomial like in normal standard phase one, and therefore you can define some measure, like for example some space like the variable space, so the maximum number of variables appearing in any configuration of the proof. So there's been there's some very nice results that have been proved in the past. Already in 2002, was shown that for any graph G, well, that is for solution, but the degree of a PC refutation of the pebbling tautologies for G is constant. But if you, instead of polynomial calculus, you take Nullstellensatz, here a lower bound by a constant time the black pebbling. So this already shows is using results on pebbling, that it's known that there's graphs that need that many numbers of pebbles that makes a separation in the degree between polynomial calculus and more recently, you can see this is an improvement of that result. Susanna or Jacobo Torán proved that for the reversible pebbling, so the weakest of this, exactly coincides with Nullstellensatz. So you can say at the same time, space and time t, if there's a Nullstellensatz refutation with degree and size t plus 1, by the way, so this improves this result in two ways. First, makes it exact, and second, it's the reversible pebbling game, which is weaker than. And with that, they prove some strong size degree trading. What we do, I forgot to say that this is John Ward, my student Lisa Riyasa, is that for the monomial calculus, the one in between, which will prove very similar results than for the reversible pebbling, but for black pebbling. So that if you have a monomial calculus refutation of the pebbling formula with degree S and size T, then there's a black pebbling strategy with space S and time plus S. And if there's a black pebbling strategy with space S and time T, and then there's monomial refutations having simultaneously degree S and size. This is not as nice as in the other paper because I'm measuring monomial calculus size as polynomial calculus size. It's different than the Nullstellensatz size. So here you count every monomial in the proof. And for example, if you have to multiply an axiom times a variable, and then another time, and then another time, you count it like 3, not just one. So, so how does it go? This is the easier direction. We use the equivalent notion of white pebble, and we prove that for every pebbling configuration, we can derive this monomial. This monomial is just the product of all the vertices with pebbles on them, and with something. And yeah, result. And this is not hard to see because inductively, pebble placement is trivial because we're starting. We can have a pebble configuration, put a white pebble in another vertex. This is just can be done by multiplying multiplying a monomial what we have times the new variable with the new white vertices. And pebble removal is also very easy because if we remove a pebble, then all the predecessors have to have a pebble on them, and we can derive the new monomial here just by a linear combination with an axiom times a variable. It's also allowed. Okay, for the other direction, which is more interesting, I use what I call an input monomial calculus refutation. This is the same concept as input resolution. And in input resolution, you have like in every derivation step is following what you've done so far and an action and an action and so on. This is not complete, but it's complete for Horn clauses, Horn for instance. And so here's this definition. So it's called an input refutation if there's a sequence of monomials, so that the first one has to be an axiom, therefore it has to be an axiom monomial times. The last one is 1, and each monomial is obtained by multiplying the previous one times a variable, or by a linear combination with this one and an axiom. And I would call these monomials as the backward. Much easier to see it with a picture. So in a monomial proof, we have its backbone in red, which is only made of monomials, and instead you can either have a multiplication with a variable like in or a linear combination. This and exactly these monomial refutations, the input monomial calculus refutations are optimal for. So if you have a Horn formula, this is one with at most one positive variable in every clause, you can translate it to a set of polynomials, and so that these polynomials have at most 2 monomials in each axiom. And we can transform this, or from this proof P, we can make a new one with the same degree at the same time, which is input. And the proof of that is by induction on the number of multiplications of these rules. So you're applying a multiplication rule to a monomial. At the base case, I'm also interested to say, base case, no multiplications, we have Nullstellensatz. So in that situation, yeah, there is a linear combination of axioms times monomials that adds to 1. And right, as I said, since it's a Horn formula, all these polynomials times monomials have at most 2 monomials, and I represent them here with proof by a pair, by the pair of the monomials. I consider a monomial as a set of particles. So the one monomial is represented by the empties. Also, the coefficients, as we're translating a formula, are 1 and minus 1. And there can be also clauses without negated monomials, which would be negated variables with single monomials. So now you can see that there has to be a sequence of polynomials that have this kind of representation. So why is this? Because the linear combination adds up to 1, and therefore has to be one polynomial with the empty monomial, because otherwise we would have variables everywhere, and we would have a satisfying assignment for all the polynomials. And this one has to cancel because at the end it is 1, so the M1 has to cancel with some other polynomial. So there's been another monomial M1 somewhere, and this one maybe has another M2, and this has to cancel 2, and so on, until we reach to some monomial M that has to be one of the axioms, or the axioms multiplied times. So this gives us a backbone of an input MC refutation that will take this, which is this monomial that leads that. And yeah, also I say in an input refutation, of course, you cannot have the monomial twice in the backbone, because otherwise you can short. And for the induction case, we take the first multiplication. So in the original proof, so it's a variable times a monomial, and there's, before we multiplied x times m, we have to derive m, but this is just what we did before. It has to be by the same argument, some chain like this, with 2 monomials, deriving it. Produce a backbone, and then we use the fact that adding this new axiom, this axiom is just one monomial, so this formula is still whole, and therefore we can use induction hypothesis, and the new proof looks like this. We derive this backbone m, and then we multiply with multiplication, and then by induction hypothesis we can do it. So immediately we get, since pebbling formulas are Horn formulas, that for every single direct acyclic graph, there's a monomial calculus refutation to the most same size, and therefore we get, if you see the parameters in the proof, if we can extract out of it just by going down the backbone, a refutation, because either it's a multiplication and that's adding a white pebble, or it's a linear combination, and this can be only with an axiom of this kind. The only variable that can disappear is the linear combination with the monomial is xp, and all the predecessors are already there, so we can take out the white pebble. So this shows really that for the monomial calculus, it's exactly the black, not without taking the time. And we compare with these results, it's like improving the old one in a different way. They improve by doing for Nullstellensatz, by improving the lower bound, and we consider the black thing and say, okay, we can even get stronger. This proves degree separations by using the pebbling pebbling results between Nullstellensatz and Monomial Calculus by logarithmic factors, because that's the best separation that one knows between reversible pebbling and black pebbling. And I'd like to mention here that Mate and Makusa have a better separation. It's polylogarithmic, very different. And also we get size degree trade-offs for monomial calculus using the known time space trade-offs for black pebbling. Interesting thing here is that for black pebbling, one knows very strong trade-offs, even better. So if we look at this, so we have, okay, the degree for Nullstellensatz is exactly reversible. The degree for monomial is exactly black pebble game. So what about the white black pebble game and monomial calculus? So as I said, the degree for polynomial calculus is constant. So the degree doesn't work, but you see here, one can get the variable space. And it's known that just now for resolution is ordinal so that the variable space is greater or equal than the black-white pebbling number. Less known, Alexander Hertel proved that also the other direction. And also it has been observed but also in other places that for any unsatisfiable formula, the variable space in polynomial calculus coincides with the variable space in resolution. It's the same. So if we take the variable space and we observe that the results for reversible pebbling and monomial calculus work also for variable space, we get this nice characterization, which is the three systems. The variable space is exactly the pebbling number in the three different so this is the end of my talk. I would like to also say, disclaimer, that a couple of weeks ago, we published in CC this report, the results I explained together with some other things, and unfortunately, in this result that I claim there, there's a mistake in the proof. So the results still. So I send a comment to ACCC, it's up, but in case anybody of you read it, I think it's here. Thank you.
And the time we ready for two very quick questions. The moment I say we're running out of time, questions.
Right,
Okay, so then let's do that.